probably going to be something like size of a page times the new number of pages. And you might want a cast here as well, so whatever the cast is going to be. One problem that you might encounter if you're doing dynamic memory for your actual page like names themselves, like big animals that are going in those pages, if you're doing dynamic memory on those, you might need to do some initialization on this if you're making something bigger. So if your cages are getting bigger, if your array cages is going from some smaller size to something that's like larger, then the idea is what's stored in here if you use reality? Anything? Garbage. So if you have something that's like dynamically created, you'll probably want to make all these guys point to null. That's going to be like a safe thing to do. It's a good idea. And even if you're not doing this dynamically, even if you're doing this statically, it still could be that you're creating a lot of strings in here that have like random bytes inside them. So you'll probably want to null terminate these guys. So just like as a pro tip, what you'll probably want to do with this section is some initialization. All right, and then the other thing I want to mention is if you're doing dynamic memory, the other thing you need to worry about, like if you're dynamically creating the strings anyways, so like this is like if your strings are non-static. I know some of you guys are doing static strings, which that might be a problem in some of the big test cases. I'm not 100% certain yet. Which there is a tricky, with air quotes, case that's uploaded to web courses if you want to go ahead and take a look at it. It has like a few minor things. So you can go ahead and look at that anytime in free time. But if you're going from like a bigger array to like a smaller array, so like the idea is like we're going into this like small section. If you're doing dynamic memory, this stuff here will be kind of lost, so you might need to free this. So this may need to be freed. And that's like if you're using dynamic memory to store the names. So if the names are stored in dynamic arrays, like dynamic character arrays, then you'll probably need to do some freeing on these values just to ensure you're not leaking memory. If you're doing static arrays, this is probably not necessary. So this is like really important for dynamic memory people, and this is like kind of important for anyone. All right, so the warm-up problem today, we'll do something very simple. I know I said they've always been simple, and then like people like cry and it's taken like 25 minutes to go through the whole thing. So we'll try to make it a little bit easier today than the previous days. All I want to do is just make a lot of names dynamically. I'm just going to read in a number, and that number is going to say how many names to read in, and we're going to type in that many names. We're going to store them dynamically, and then what we're going to do is print them out at the end. So we're just going to read in names, store them dynamically, print them out. Hopefully that won't be a problem. So I'll write that down. So read in names, store dynamically, print out names, and then free the dynamic memory. That's going to be the goal for this warm-up assignment. That being said, I said that it's really simple. I imagine there's still going to be a large portion, probably at least a third of the class, that's unable to do this without assistance. And it's okay if you're in that third, or however large that is. So the point of going to class is learning how to do these things. So if you know how to do it already, not that you shouldn't show up to class, but it's like that is the class I guess is working, hopefully, fingers crossed. How do I put it wrong every single time? It's not even a USB. All right, so I already wrote up a lot of the stuff, basically a large comment at the top. So the input format is going to be the number of strings. I'm just going to refer to that as like n. And then what we're going to do is we're going to read in string 1, string 2, string 3, all the way to string n. These are going to be strings, so there's going to be no white spaces inside them. Example could be like 3, and then we have Bob, Alexander, and Carol. I don't know why I didn't do ABC this time, but I didn't. And then the idea is that we're going to output those names. So we're going to output Bob, Alexander, Carol. We won't output 3. And we're going to assume that there's no more than 1,000 characters per name. So this is my main function so far. Oh, let me fix that. All right, there we go. That looks good. So we're gonna complete this. So what is going on here? So we're including standard I/O, we're including standard lib because we're going to do dynamic memory stuff. We're including string because we're probably going to use some string things. We're defining the max name length to be 1,000 because we said no max name is going to have more than 1,000 characters. And of course, like if you guys are just joining us, this is a warm-up problem. All we're trying to do is read in strings and sort them dynamically, just kind of like getting us ready for a little bit more dynamic memory before we move on to binary search. We're just still going to have a little bit of dynamic memory just to manage it. All right. So we read in the number of strings. We have int num strings, and we scan them in here. And we use ampersand because we're reading into something that's not already a pointer. And then we have this strings. And why is strings a char star star? Yeah? So why do we need two references? It's really not two references to strings, it's two references to characters. But like, why do we need two references? Like, what does the reference give us? I guess, yeah? Okay, so one pointer is because we want to have an array of strings, and then the other pointer is because each string is an array of characters. Yes, that's exactly correct. We're having an array of arrays, so that's why we do a char star star here. So then when we do the calloc, you want to make sure that when you calloc or allocate your memory, whatever you're going to be doing, you want to make sure that you're always casting to whatever type we're using. So because we're trying to do a char star star, I want to make sure that strings, when I do the casting, is char star star. You always have the cast same as the type of what that information is. You don't do char star star is equal to calloc, that's silly. You don't want to ever try to assign a type, like you don't want to go ahead and put information into a type. That doesn't make sense. You were able to put information in variables, but types should not be like modified. You can't really modify them. You don't ever say int is equal to 7. So we want to do something like strings, which is the variable of type char star star is equal to, and we'll do an allocation. So we say what the type is to go ahead and cast it, and then what should I put in these ellipses? Calloc? Okay. Someone said calloc. We're going to do calloc. And that's it? We're done? Yeah? Yeah, we need to tell it kind of the amount of memory. So how does calloc take in the amount of memory that we create? How many arguments does the calloc take in? 2. Okay, what are the 2 arguments? Is it destination? So realloc takes in like a source information, but calloc, the destination that calloc gives you is actually the return. You don't tell it the destination because it tells you the destination. So you can't really say this is like my destination that I want to like write to. It's going to say this is where the memory is stored at. The computer kind of has control over where things are going to be put at. So unfortunately, destination isn't one of these. Then what information does calloc want if it wants 2 things and not one? Like one of them is not destination. What's that? We want the quantity and then the size of each item. So what is the quantity? How many items do we need here? Num strings, because that's how many strings I'm going to be creating. And then what's going to be the size of each one of these strings? Size of, I like basically told you by asking, size of what? Char star. So pro tip, whenever you're creating like an array or something like that, the idea is like this is going to be your array of things. So it's always going to be a reference to the type that you're trying to create. So that means there's always going to be kind of one more star here than what you have over here. Because this is going to be a reference to the thing you're creating. In this case, we're trying to create an array of strings, which a string is really a char star. So that means every item needs to be a char star, but it needs to be a reference to that. So that's why we have char star star. And then the size of is going to be just a char star because each one of these elements is going to be a string. Hopefully that kind of clarifies things. I know some people still have a little bit of problems understanding that exactly. So then what's the next thing I need to do? So I created, in theory, my array of strings. What's the next step? Yeah? So we're going to loop over and enter the names. What should we loop up to? The number of strings, very good. And I do do I++ here, right? All right, that looks pretty nice. So, what, I do like scan out? That's how we read strings in, right? and we do like %s, do you guys agree with that? Scan %s. I need to say where to read it into. Where do I read it into? Strings of I is what I heard. Alright. Who thinks that this is a good idea? Raise your hand. What? Alright, who here thinks that's a bad idea then? Raise your hand. Like 2 people. Okay, so a lot of people are just on the fence. I don't know if this is good or bad. Let me have my compiler tell me if there's something broken, right? Don't do that. Like, you're gonna need to be able to like figure out whether there's a problem or not without a compiler on the foundation exam and without a compiler on the test and final exam. So, well, what would be an issue if we tried to write into strings of I currently? Would there be a problem if we're trying to write to that location? So what is strings of I supposed to be? So what is strings supposed to be? Let's go with that. Strings is what type? Is it a char? It's a char star. Is it a char star? It's a char star star. There's 2 stars. So it's really a pointer to pointers. If I then do a dereference, if I do bracket I, then what type is it going to be? What is the type of strings bracket I? It's just a char star. The brackets will remove one of those stars because it will do a dereference. And so normally strings is a reference to a reference of characters. And so by removing one of those references, we're now just a reference to a character. There's a hand up. So do I need to add another dereference to this? So normally, if we're trying to read in a single string, we would want to read into a reference that is a character. If we want to read like a single, not a single string, a single character. If we want to read in a single string, we also just use a reference to the character. Because like, whenever you've done like reading in before, we've done just like the string name, and like that's worked out. And the thing is, like for scanf, you don't need to use ampersand when you're reading a string using scanf because the strings are already references. So strings of I is a character array. It's already a reference. You technically don't need to use an ampersand. So this is actually fine the way it sort of is, but there's still actually a problem. This is going to cause probably a very fast segmentation fault. And if you don't believe me, let's go ahead and try running it. So GCC, I call this array of strings. We'll run it, and we'll go ahead and type in 1 Alice. Wow, that actually worked. I don't like that. Let me try doing that again. Did I write it? I did write it. All right, I'm gonna try maybe Alice and then Bob. Okay, it didn't work. So it stopped early, and it's not because it finished reading all the names in. It's segfaulting and it's not telling me. I bet it's because I don't have enough room, maybe. I don't. Why is it not telling me you segfaulted? Let me see. Try running this one more time. To Alice. All right, fun, fantastic. Let's double check that it's actually reading in things. I'll go ahead and print out what I is in each one of these instances. So printf %d. This is what happens normally when you are debugging your program. We'll do I and then we'll do num strings. I just want to like emphasize that it's not exiting the loop here early because of sun. Let me go ahead and make it really big. So we'll do 100 and we'll do Alice and okay. So definitely, it doesn't like doing what it's doing, but this is strange behavior. So the issue that we have is we can't really read into this location. Maybe scanf just decided to quit because it doesn't like what's going on. We can't read into this location because we actually don't have any memory for it to read into. Like if I printed out what strings of I is, like I could print out the pointer of strings of I. Like where is it actually writing to? Yeah, one moment. Strings of I, yes. We don't, so %s doesn't actually read spaces, so that's not going to be the problem. If I compile it and I run this, if we look to see what strings of I is, so again we'll do like less value, we'll do 10, and then we'll do Alice, and I didn't write my program, so of course it doesn't decide to print anything out. Write, compile, I meant to do a %c pointer, compile, run, 10. All right, and so do you see where it's writing to right now? What's the pointer that it's giving me? Nil. So nil means bad. Nil means we should not be writing to that location. And so it's causing issues. So what we really need to do is we need to allocate room for that spot before doing this read. So we can't write into strings, and this is like the thing I was trying to get at. We can't write into strings of I because it hasn't actually been initialized yet. That information is basically garbage. We need to go ahead and say, you have some amount of memory. We need to give strings of I memory so that way we're able to write to that location. So let's go ahead and do that right now. We'll do strings of I, because it's a pointer, and really right now it's not pointing to anything useful. So what we need to do is we need to point it to some section of memory so that way it's able to go ahead and write into some place that we can actually read from. So we're going to do, what type should I pass this into? It's a char star, very good. And why is it a char star? Because it's a string?
Because strings of I is RBG references.
Yeah, so strings of I already references it once, so because it's char star star, by using bracket I, it becomes just a char star. And what do I put here for the allocation? Calloc or malloc? Alright, we'll do malloc. Malloc, and then what's the size of this? Max game length, that's it? Plus one, why plus one? Null terminator, and that's all I need to do? Okay, this technically works, but it's like really inappropriate. There's one more thing we really should be doing. And almost any time you do an allocation, we need to do size of. So what we need to do is we need to multiply this whole thing by the size of something. What should we multiply by the size of? Yep, size of star. And that will go ahead and create a character array that's of length, max name length plus 1. And we can then write the contents into the string. So let's go ahead and compile this, and we'll run this, and we'll do 10 strings. Oh, we'll not do 10, we'll do 3 strings, and then maybe it won't like freak out. Oh, look at that, it's Alexander. Okay, there we go, that's exactly what I wanted. It read in every string, it didn't go immediately to output. So now we have the ability to print this content out. So let's do so, hopefully. Okay. Technically we're wasting memory. Do you guys want me to fix the memory, or do you want me to do the printing first? Who here wants me to fix the memory issue that we have? Alright, cool. We'll do that. I'm not going to ask you the other one because I saw enough people that are awake to raise their hand. So the problem is strings of I is way bigger than necessary. So what we can do is we can shrink it down. And how big does strings of I actually need to be? So right now we're making 1,000 characters for it. Does it need to have 1,000 characters though? How many characters does it really need? The length of the string plus 1, yes. So we're going to do strings of I is equal to realloc. We should cast it. What do we cast it into? Char star, very good. And then what are the arguments for realloc? We're doing all 3 allocation functions in one function. This is great, or one code. So what are the arguments for realloc? Yeah. Is it the new size in total? So what does realloc do at a high level? Can anyone explain to me what's the purpose of realloc versus the normal allocation functions? Yeah, so it rewrites the memory to potentially a new location. But the idea is that in order for it to rewrite it, it has to have what? And what does it have to know? Yeah? It has to know where the previous section of memory is at. So you have to tell it in the arguments, where is this memory located? So I'll give you a really big push, and don't worry about knowing the exact arguments about this for the foundation exam. We actually put the arguments for you on the foundation exam formula sheet, so that should be helpful. But it's good to know anyways. So it's going to be the pointer to the old section of memory. Where's the old section of memory at? The new string? The previous string. So what's the previous string then? Strings of I, really? We're trying to write strings of I to strings of I. I think I told you this is like an unsafe thing to do. I'm not going to worry about it right now. You won't need to worry about it for your homework assignment. So what we're going to do is we're just going to take strings of I and we're going to resize it down to what it needs to be. So this is like a memory vulnerability, but I'm not checking null in the other location, so why am I going to begin checking null right now? Then what's the next thing I need to do? What should I put after the comma? What's the next thing we need to know? The new size. So what's the new size going to be? The Sterling of strings of I plus 1 And then what did we miss? Size of, alright, so size of what? Times size of, or what was the trick I just told you? Like, how do I get the type here based off the type at the beginning of the line? It's going to be size of char, because the idea is we're creating an array of characters, so that means we want to create characters. So we want to basically remove one of those stars, and if you remove a star from char star, it's going to be just char. All right, I'm gonna maybe break this up into several lines, so that way it's easier for me to read. Yeah, it's still disgusting, but it's better. So we reallocate the strings of I to strings of I, and we give it the appropriate length, and we multiply by size of char. The size of a char is normally 1 byte, so it's probably not necessary to do that multiplication, but whatever. So then we're gonna print out the strings. So we do for int I is equal to 0, I is less than the num strings, I plus plus. And then what we're going to do is print f %s, and then we do strings of I. And then the last thing I want to do is free the memory. So what do I do to free the memory? We need a for loop. Why do we need a for loop? We need to free all the strings, that's right. So num strings of I plus 1, or I plus plus. We need to free all the strings because we allocated all the strings in a loop, so we're probably going to have to free all the strings in a loop as well. So what we're going to do here is, do we need to free strings of I twice because we did 2 allocations for it? What would be the problem if I try doing free strings of I, free strings of I? Yeah, I'm dereferencing it really after I free it. But really, this is more commonly known as a double free. Double frees are bad. They're the worst Pokemon. So what we want to do is not actually free strings of I twice. We actually want only free it once. Now, why do we have 2 allocations here, but we only need to free it once? Can anyone explain to me why there's 2 allocations but we only need 1 free? Yeah, in the back.
It's because when you reallocate, it already frees the excess stuff.
Yeah, so the realloc will do an implicit free and an allocation, so it's already doing 1 free for us. So a realloc effectively doesn't increase the number of frees we need to do because it kind of cleans up the old memory for you in the first place. So we only need to do 1 of these. All right, and then what else? Is that the only thing we need to free? What else do we need to free? We need to free strings. All right, so let's do free strings here. All right, I hear people snickering. What did I do? Yeah?
You're supposed to put that after.
Yeah, that's correct. We need to do it afterwards. And why? What would be the problem if I freed strings first? In the back or in the middle?
When you want to go run that loop, you're freeing something that's already free.
Yeah, so I'm trying to dereference strings, but strings has already been freed, and that's really known as a use after free. So I'm doing a use after free, and that is a violation. And this, in theory, should be the correct code now. Let's compile it. Let's run it. 3, Bob, Alexander, Carol, whatever. She's capital. All right. And it prints them out. And we can double check that we have no leaks. So Valgrind or grind a.out 3, Bob, Alexander, Carol. All right. And it says there's 0 bytes and 0 blocks. There's 9 allocations, 9 frees, and there are no leaks. Cool. All right. So that is that example. I'll upload this later. What we want to now work on is an array list example that we talked about at the end of last period. You remember that? What was the whole point of the array list? Can you guys remind me? So the array list was supposed to do what? What's the benefit of using an array list over a regular array? That's right, there is none. No, that's not the case. what is the reason? Yeah. Yeah, it's unbounded. A normal array has some limit to it, especially if you're doing it statically. But because we're using dynamic memory, we have the ability to kind of have some unbounded array-like behaviors. So what 3 pieces of information do we need to know for the array list? Yeah, in front. So we need to realloc. Yeah, so we do want to do a reallocation of the array list. The idea is that we're going to realloc some piece of it. What piece of it do we end up reallocating? There's three pieces to the array list. So we implement inc with three basically members inside the structure. What are the members? So 3 members. We have one what in the back?
One size.
We have a size. What does the size represent? So there's a size and there's another value. There was another, so this was an integer, there was one more integer. What was the other integer called? Yeah? Capacity. So what was the distinction between size and capacity? They sound like the same thing, right? Because normally if you say like the size of a water bottle, it's like also the capacity of the water bottle. So what is there a difference? Yeah. Oh, okay, so like one of these should be smaller than the other one. How we like to think about it from the array list perspective, like this, like there's like the amount I see what we're saying. So we're saying that like there's something that's like how big does this element take up with respect to how much can something fit. So that's a little bit ambiguous. We should probably not use water bottles as an example. I'll try to keep note of that in the future. So the capacity in our sense, is really kind of like how much we can fit in the water bottle. I agree with that. So this is like how much we can fit in the water bottle. But the size is like maybe a little bit misleading as a name. What the size actually is supposed to represent, it's really supposed to represent the volume of water. Like how much did we fill this water bottle currently? So size again, a little bit misleading here, but basically it's supposed to represent the number of elements inside the array list. So there are some times where we run into issues where we have to like kind of change the water bottle size because the water bottle might fill up completely or something like that. And then what we'll end up doing is like some sort of like reallocation of something. So what's the third thing am I missing here? So I have like an int and an int. Is this really an array at this point? Does it have the ability to fit multiple values in here? Looks like you can only fit 2 things inside here, so that's not good. So what do I need? I need a third thing. What do I need? Yeah.
The number of indexes?
The number of indexes? The thing is, if I have just a number of indices, that sounds like just one value still. So maybe not number of indices. Yeah, in the back. We need a pointer, and we need it to be like really representing the array. So we need like the array, and yes, this is going to be a pointer to the values. So I don't want to say like the number of values we have here. I really want like either an address of values or a reference to the values. That's like really kind of what I was looking for as the answer. So these are the 3 pieces that I need to properly implement an array list. I mean, obviously I need to have an array if I want to make an array list, because why else would I call it an array list? Yeah, you know, it's got in the title. But then the size and the capacity are the 2 things that people, I think, have like difficulty with normally the most. And like figuring out which one's supposed to be which. So the capacity is just kind of supposed to represent kind of like, again, like the total that we can fit. This is like the capacity of the room. And the size just represents like the size of the party. How many people are coming to this party? How many people are like, you know, currently there? The functions that we talked about we want to do with an array list, like we want to be able to, so the functional members, we want to be able to create one, and that was pretty easy, I did that in class. We want to be able to destroy one, but we also want to be able to like add to the end. What did I call adding to the end? Do you guys remember? Appending, very good. Yeah, append. So we want to be able to append, which means add to the end of the array list. Where is the spot that we add to? Do you guys remember when we do an append? I think I mentioned this in class. So let's go ahead and write up what the append function looks like at a high level. We actually didn't get to code this in class, so it'll be good to go ahead and like kind of write this out. So when we're trying to append something to the list, like this one's like pretty easy, this one's pretty easy, this one's like a little bit harder. So what we do for the append is we have our list, and we have the value that we're going to be inserting. The first thing we want to do is obviously insert the value into the list, right? Okay, that's really the whole goal of this. Like we want to insert the value to the list. So what's the problem with just saying like, put the list, put the value at the end of the list. So we'll say like, the list at the end is equal to the value. Like what problem might we run into by saying this statement, this command? This is like pseudocode, by the way. I'm not like actually, this is not going to be real code. Yeah.
Could be overriding something that's already in the list.
Well, like if we're doing it at the end, like maybe not. Like let's call this like maybe first empty spot. Do you agree that the first empty spot is probably where we want to write it? We shouldn't overwrite anything now, right? I think we agree that we're good with not overwriting stuff. All right. So we're not overwriting stuff. Is there a problem then? Yeah.
Is it the null terminator?
The null terminator? Okay, so if we're doing strings, maybe, but this one hopefully won't be a string. This will be just like a normal array. So yeah, like if we had like a string that we're trying to do, we would need to also write the null terminator afterwards. But like, let's imagine that we're not doing a string. Let's imagine that we're just doing integers. The reason why we want to know the null terminator in a string, by the way, is because we don't know the size of that string. So the null terminator kind of gives us the information as to what the size is, but because we explicitly store the size, we don't really need to store the null terminator for the array list example. So then what is the problem then? Yeah. There might not be an empty spot. That's exactly what I was looking for. So like how would we not have an empty spot? So if we think about this like from the party perspective, if we have like a room and we have like a whole bunch of people in there, why would there not be a spot for a person? If the room is at capacity, exactly. So like it's like a pretty poppin' club or something like that. I don't know. But what do we want to do then to fix that? We want to increase the capacity. So if the thing is at capacity, how would I know if it's at capacity? So if what? If the size is equal to the capacity, exactly. So if size equals cap, then we need to increase capacity. All right? Now that we've increased capacity, we can go ahead and fix this. We insert the value at the end, and then what do we need to do at the very end? So we modified, yeah. The null terminator? Well, we're not doing strings, let's not do a null terminator. So we've updated the capacity here. We've updated like the array of values here. What have we not modified at all in this list structure yet? So we've touched the capacity and we touched the array. What did we not modify? The size. So what do you think we need to do then for this thing? Why do we need to increase the size? Because we added someone, right? We added someone to this party, which means the size is increased. So we want to increase the size. All right. And this is like at a high level what your array list append method does. It will check to see if we're full. If we're full, it will increase the capacity. Regardless of whether we were full or not, we'll insert this value at the end, and then we'll increase the size to go ahead and ensure that we know how many elements are correctly inside this room or inside this array list. So what's the first empty spot? This is like maybe something that's not clear. This is like pseudocode. We need to go ahead, like for the purposes of C, we need to actually put what we need to do here. Yeah? What do you mean the beginning of the index?
Or the beginning of the array.
But like if we store something at the beginning of the array, like if we put something there, then when we try to append another element, then we won't be able to put something there. It won't be empty anymore, right? So it might not be it can only be the beginning of the array once, and exactly once. Because every time after we try to insert an element, it won't be that location anymore. It might be some other location. So then what? Where would it be at? Yeah? The size of the array plus 1. I like that thought process. Let's go ahead and do an example. So let's say that we have this array. What's the capacity of this array? Let's do this. What's the capacity of this array? It's equal to 6, right? There's 1, 2, 3, 4, 5, 6 spots. All right. What's this index? 0, 1, 2, 3, 4, 5. What's the size? Is the size 5?
Size is 6, right?
How many elements are in this?
6.
Maybe 1. If that represents an element, then there's exactly 1 element in our list. All right. So what's the first empty spot then? Is it size plus 1? Where's size plus 1 at? Size plus 1 is 2, so that'd be there. So someone said it's just size. Why is it just size? because the arrays are what? They're zero index. They're zero index. Because they're zero index, all the elements are going to start at 0, and then if we have size number of them, they're going to be at 0, then 1, then 2, then 3, and the last element goes at which index if we have size. Like if there's size number of elements, what's the spot with the last element? Size minus 1. It's size minus 1 because it's 0 index. The idea is like if it was index based at 1, it would be 1 to size. But because we shift everything down because we have a 0 in there, it goes from 0 to size minus 1. So we go to size minus 1. Size minus 1 is the last location we have an element. So then what's the first location without an element? Size minus 1 plus 1, right? Because we go 1 index over. So we go that 1 index over, we see that this is going to be empty and we insert the element. But if we do size minus 1 plus 1, it's just size. So size is going to be the location that's empty. Oh, the first location that's empty. All right, so then this first empty spot, what are we going to put here? Just size. All right. Now the question is, how do we increase the capacity? And I'm hoping that we'll be able to go over this in more detail. There's 2 ways that we can do this, and I think I might have mentioned this in class. What are the 2 ways you can increase the capacity? Yeah, in the back. So we'll always use imagine realloc, but like when we realloc, what do we want to do the capacity? Like, so what would be? Let me move over here. So if we have like a capacity of 10, what do we want to change the capacity to if we wanted to increase the capacity? Does anyone have any thoughts? Do we want to change it to 9? No. So at least 11, hopefully. If the capacity is 10 and we're full, we have 10 elements in there, we need to have at least 11 to go ahead and support this. Is it a good idea or a bad idea to make it 11? It depends. But, so for this increasing capacity, there's 2 rules of thoughts. So there's one option is to just add 1 to the capacity. So that's like one thing we could do. How often do we need to resize the array if we always plus 1 the capacity? Like how often though? Is it like every other time?
It's every time.
It's every time. Every time I add an element, I have to increase the capacity. And that can be expensive. And the reason why is because this will involve some reallocation. And reallocation, in bad cases, has to move the memory from one section to another, which won't be good for us, because moving that memory can get very expensive as we get more and more values. So then there's another thing we could do, which is to do something else with the capacity. What do you think the other thing we could do with the capacity? And we're not adding 1, yeah? So we could try adding a larger amount. We could add like 2 or 3 or 10 or something like that. You don't want to add too large, because if you end up like adding 100,000, but you're only going to store like 1 value, that's going to be like a waste. But the problem is like if we add like a small amount, like if we add 2, then that means we have to resize every other time, and that doesn't really give us a huge speed up. I mean, that is still like faster, but like it's still going to be probably really slow in some cases. And we'll be able to do some order analysis to show like adding 2 might not necessarily help with that too much. Even adding 10 isn't super great if you like do enough insertions. So, all right, if we're not adding like 10, we're not adding 2, then what could we do? Yeah. Size of int? I wouldn't like add size of, because if we add the size of like a data structure, that's like adding like a fixed value still. Is there something else we could do? Yeah?
Could you double the capacity?
Alright, so instead of adding, we could try multiplying. Like that's another thing we can do to increase things. So we could try multiplying by 2 to the capacity, and really, this addition, it doesn't have to be +1. You could also try to do like adding 2 or adding 3 or something like that as well. But here, we don't have to just try doing ×2. Some people actually do ×4 capacity, and this is a very aggressive thing to do. So there are some drawbacks to using this method. So this one, we don't have to do that many allocations, and we'll talk about how many allocations we need to do later. But my question for you is, like, what is the downside of doing this doubling of the capacity? What do we end up having problems potentially with? Yeah. We're going to use a lot of memory. So this is like really a memory versus runtime trade-off. So the idea is that we can speed up our program, but we have to go ahead and do some memory sacrifices. Now, in the olden days when you had computers that had very limited amounts of memory, this was obviously not very appealing, and we would rather just let the program run for a while. But with modern computers where we have just so much more memory that you're not really using it all, this option 2 is actually much more appealing, and this is what like most people will end up using in nowadays. Because like you can arguably prove theoretically that this is actually not that much more memory that we're using compared to the original. So this is the option that we're going to be going with, and what we're going to do in class, and what's accepted on the foundation exam. If you try doing the first one, you'll probably get in trouble. All right. So let's actually finish coding this up. So in the last class, array list .c. All right. And so right now, this ArrayList.c, it has the creation function, and it also has the destroy function. Hopefully this looks familiar. And what we need to do is we need to create this add to list function. We need to go ahead and tell it what list we're using. We're using like, we're using some list, some pointer to a list, I guess. And then we also have some value to insert.
I don't think this was this section that you wrote this.
Crap, really? But this isn't section, oh fuck. This is section, yeah, this is section 4, isn't it? Did I write this in section 1? Oh, I hope I didn't write this in section 1. All right, well, if I wrote this in section 1, then let's see what I wrote in section 1. So CD into S2. That doesn't look right either. All right, well then we'll just go ahead and type up, reset. We'll just go ahead and type up the array list from scratch, because that doesn't sound too bad. CD S4. Vim array lists new .c. All right, so the point of the array list is that we want to have the memory set up in an ordered fashion using the array. We want to go ahead and, I'll just go from the top. We want to create the array list structure. It needs the 3 components. It needs the size, the capacity, and the array. So let's go ahead and get that going. So struct array list. Bless you. And then what we're going to do is we're going to do int cap, int size, and an int star array. And what we're going to do for this very simple array list, we're going to go ahead and read in numbers until -1 is read in. So int main, int value, and what we're going to do is we're going to keep reading the value until we get a -1. So we're going to say, we can really do a do while loop. Do I want to do a do while loop? All right, whatever. I haven't done a do while loop in a while, so this will be a trip. So do while the value is not equal to -1. And we'll read in the value, so we'll do scanf, %d, ampersand value. We will then add the element to the array list, so we need to create the array list, let's do that. So we'll do array, struct array list pointer list, and we will just add the element to the array list, so we'll do append to list, comma, value. So we'll need to make an append to list function. I'll prototype that. Oops. So this is going to be void append to list. And this is going to be struct array list pointer as the first argument, and then type integer for the second argument. Now, this is just as a pro tip, when you're creating the append to list function, like when you're trying to like append to your array list, it's actually nice to return a 0 or 1 depending on whether you succeed or fail with doing this insertion. And the reason why is because you can fail when you do your reallocation, when you try to resize your array. So in practice, it's a good idea to have this be a non-void function, but I'm doing this as a void function because I'm going to assume that this always works. But in practice, it is good to use a function with a non-void return. Just to go ahead and give back to the user whether you succeeded or failed, or the program whether you succeeded or failed. It could be the case that you ran out of memory. Maybe you have like a really small machine and you're trying to double every single time. But hopefully that won't be the case. Then what we need to do at the end is we're just gonna maybe return 0, or what we could do is we could do what we did before, which is like print out all the values. So let's go ahead and make like a function that will print out all the values in lists. So we're gonna do like print lists, and we'll do just the list itself. And yeah, so we need to do more things as well. Let's go ahead and just, do I want to do the append to list now? We'll continue writing out the function. So we are missing some things from this function. So are we going to be able to modify the list as it stands currently? Like, are we able to do the append to list with just the list pointer the way it is currently? Why not? What is, yeah? Oh, okay, so we didn't create the function, but hypothetically the function exists. Would there be an issue? Yeah, in the back?
We haven't, so we haven't allocated memory for the list, right? It's pointing at nothing right now.
Yeah, so right now this is actually a dangling pointer. We can't use it because it's not pointing at anything useful. So what we actually need to do first is we need to tell it what list to use. Like we need to point list at something. So list is currently a dangling pointer. So the first thing we really want to do before we enter this loop is we want to go ahead and create the memory for the list. So we'll do that by saying list is equal to create list. And now we'll go ahead and initialize the list hopefully and have everything set up for us to begin going. Like, I didn't even like set like the size equal to some value or the capacity equal to something. I had no clue what could the values be, especially given that like we don't know where it's actually pointed at. So let's go ahead and create this create list function. So we'll do, what type of return does the create list function need?
Void.
A list pointer,
It needs to have a list pointer. Like what type of list pointer?
an array list pointer.
Array list pointer, but really it needs to be a struct array list pointer, and then this is going to be the create list function. Ew. All right, that's another prototype we need. Oh, we also need the print list prototype, so we'll do void, because we don't need to return anything from the print list, so print list, and then it has a array list, a struct array list pointer as the argument for the input. All right, so if we're creating this list, what do you think we should also do? We should probably destroy it as well. So let's go ahead and create the destroy method for this list. So we're gonna go ahead and do destroy. So we're gonna, this is like really simple. Print the values we read in. And then what we're gonna do is destroy the values and the list. Destroy lists. So what do I need to do for this prototype? What arguments is it going to take in? So arguments are going to be what? So what type does it return? What do I need from the destroy list? Void. I don't need anything. All right, and then destroy list. And then what argument is it going to take as input? The struct array list pointer. All right, let's go ahead and create these functions now. So 5, not 26. I think it's like read 45. There we go. What's up? Yeah. So let's go ahead and do this create array list function. So what do I need for the create list? Like what do I need to actually store inside this function? Yeah.
This is me answering questions, but I have a question.
Yeah. What's up?
The function later.
So which function?
If you go to the top real quick.
All right.
Okay, so for print list
Yes.
and destroy list, we only have one argument, which is the struct array list.
Yes.
Wouldn't you need to also like name that instead of just?
So if we're making a prototype, you actually don't need to put a name for the arguments that are in your prototype. That's something I think that not a lot of teachers do. But I don't actually need to say the name of these things. I also didn't name the list in the append when I didn't name the integer here. They're just saying like, this is the type that you're gonna get. You don't necessarily need to specify what name they're gonna be. They're just saying like, this is the arguments you can expect. So when we go down here and create them, when I actually create these prototypes, I am gonna go ahead and say, oh, this is the list, and I'll do that. But we don't need to actually name it at this point in time. All right, but back to my question, what do we actually need to store in this function? Do I need anything at all? Does the create list return anything? How about that? Yeah? So, okay, maybe we need a for loop, but maybe before we get to the for loop, I recommend when you're making a function with return, always make that return. Get that thing set up initially. So what type of thing are we going to return in this function? The struct array list pointer, right? So we'll create the struct array list. And this is going to be called list, or if you want to, you can call this like the ret. I like to call it ret because it's the return value. And then we want to make sure that we put the return at the bottom. Like I see so often people are not returning, or they're returning something that's just not the right type. Like I'll say return a pointer and they return 0. Like that's not the correct thing to do. I mean, maybe you're trying to say return null, but that's just extremely improper. You should always make sure that you're returning whatever type you are supposed to be returning. So if I say like return some pointer, I don't want to see return 0. If you want to return 0, you should return null instead, and that would be more appropriate. But in this situation, I want to return a pointer to like a list, and so I'll create a pointer to the list, I'll call it ret, and I'll return that. Now obviously, this is not the right thing to do because what is ret pointing to currently? Nothing useful. It's like garbage. This is like undefined behavior. Not a good idea. So we need to do something else. What should we do to ret? We should have it what? Yeah? Initialize. So how do we initialize it? So we could try initializing it right now. We could try saying like ret arrow like capacity is equal to something. Why do I do arrow capacity, not dot capacity? Oh, ret's a pointer, right? So if it's a pointer, you can't actually access the members inside of it. You can't access those variables inside of it because it's not actually a struct. It's still a pointer. Pointers don't have members that you can access. You have to go ahead and dereference the pointers first in order to get that. Now you could put like a whole bunch of like star dots everywhere in the code, but that's really disgusting, and it's like more common for people to use these arrows instead. So I want you guys to get in the habit of using arrows when you're trying to dereference your structs and use the members of those structs. So we want to use arrow cap. What should I set the capacity to? Size? What size? So really it depends. Like there's not like really a wrong answer to this. I mean, obviously we don't want to set it to size because size hasn't been set up yet. But like we could set it to any value we want. So we could go ahead and set this to like 10 or 100. Let's go ahead and set it to, we'll set it to like 4 to begin with. All right. And that's just an arbitrary value. You can choose whatever you want. What should I set the size to? Because that's like another thing that we need to initialize. So how many things are in our list to begin with? Remember, capacity says what's the size of the room, like how many people can fit in there, and size says how many things are in there. If this is like us creating a list for the first time, there shouldn't be anything inside here. So you are correct. It should be size is set to 0. And then what's the third thing that the array list has? So there's a capacity, there's a size. What? A pointer to the array, right? What was the pointer to the array called? Let's look up here. I called it an array. All right, so let's go ahead and set that up then. So how do I do that? Help me out here. Do I want to do ret? Did you say star? Ret arrow? Ret arrow what? Array is equal to. What are we going to set it equal to? What do we want to set the array equal to? We need to create it. This is a dynamic array, so we need to create the dynamic array. So how do I create dynamic arrays? Callic. All right, so we're going to do callic. This is familiar territory. How do we use callic? Int star, why int star? Because that's the type of array. And then we do callic, right? And then what do I put inside here? Yeah? So size of int. Is that all we need? I think we need to say how many as well, right? So how many do I want to make here to begin with? Capacity, yeah. So let's go ahead and we like to do the number first, so we do ret, arrow, cap, and then we do comma size up. Because calc will take in two arguments. It takes in the number of elements and it takes in the size of those elements. All right, and this is wrong. So why is this wrong? Like, it's really close. All of the stuff is correct, barring one minor thing. Okay, a lot of people with their hand up. Wow, this is exciting. All right, let's go with the teal shirt.
It's missing a star,
Well, where is this missing the star?
I think in front of red, maybe?
Here?
No, like in front of red arrow, red.
Red arrow, right? We actually don't need to use the star here, thank God. Yeah, so the reason why we don't need to do a dereference of the ret is because the arrow will do the dereference for us. So the arrow will do that star, so we actually don't need to include the star there. There's something else that we need to do first. There's something that we need to do at this point in the code. We need like one line of code here. What line do we need? Yeah?
Need to allocate memory for ret.
We need to allocate the memory for ret. Ret is also a pointer. This is the same problem we ran into the main function. We have a pointer. What is that pointer pointing to? We haven't told it yet. We need to do another initialization. Yet another initialization. It feels like we're always just kicking the can down the road. I won't make a function to do that. I'm going to go ahead and just do it here. So I need to say ret is equal to something. So what should ret be equal to? What should it point to? It should point to a struct array list. So how do I get it to have like a size of memory that's big enough to fit a struct array list? So, all right, parentheses. Like this is going to be another dynamic memory function, so we're going to do parentheses, calc, and then more parentheses. The reason why we're going to do this dynamically is because you can't create memory statically inside a function and then give that static memory to another function. So really what we're going to have to do here is we're going to have to create this statically, we have to create this dynamically and then pass that dynamically created memory to whatever function it tells us. The reason why we can't create static memory and then give that to another function, I can draw a picture for this. So when you create static memory, like in a function, the stack has actual functions inside of it. So it has the main function, and in the main function we have like our list in here. And then what the list is really like an address of something. It's like it's storing. And then we call our create function. Our create function will go inside the stack as well. And then that has some ret value, and the ret also has some address inside of it. Now the problem is that when we leave the create function, this information goes away. It leaves. And what happens is the next time I call a new function, so if I call the append function will go into that location. So what happens is whatever address I stored inside here, that address is also kind of like if I like have it point to something that's like in this location. So if I create some list here and I have the ret point to like that list in that location, that means this list that I have in here will be overwritten by whatever next function we create. So if we end up creating a function that is like the append function, the append is going to begin overwriting the values in the list, and we end up getting like a whole bunch of garbage inside there. So it's actually going to kind of destroy whatever precious information we end up creating. So we don't want to use static memory. We need to go ahead and make sure that this list we're creating is protected all the way down to the heap, and it's not going to be touched by anything else in the program. It's not going to be accessed by any functions that we end up calling, which is going to happen if we end up like doing this all statically. So this is why we can't really create it statically inside a function. We need to create it dynamically, and then that will end up fixing these issues. So let's go back to the laptop. All right. So then how do I do this? So how do I calc the memory for it? So what type is ret? It's a struct array list, is that it? Struct related to star, right? And then what do I calc? Like how big does this memory need to be? How many lists am I creating?
One.
I think just one, right? So one. Anything else? Oh no, what did I do? Alright, size of struct array list. Array list, there we go. Alright, and that should be enough parentheses. Alright, and that is the proper way to do the creation. The idea is we create the section for the full list. We then set the values, well, I guess really we initialize the value, we'll say. Initialize the values, and we also need to create the memory for the array itself. And then we just like return a pointer to the created initialized memory. Alright, that is the create array list. Let's do the print list now. So print list, how do I print the list out? We want to do a for loop, very good. Let me actually give this list a name, so it's going to be called list, super original. So we want to do a for loop. How far do I loop?
Until size.
Until size, very good. So we loop until whatever the size of the list is, because that's how many elements are inside there. And then how do I print out the contents inside the list? Like obviously a printf. Alright, but then how do I print out, like what is stored inside the list? You guys remember? It was an array of what? Array of integers. So how do I print out an integer? %d with a \n, and then what do I pass in here? Where am I reading from? Where are the integers stored at? The list arrow where? Array, right? Because that's where the array is actually located. It's that red arrow array, or in this case, because I called the list instead of calling it red, it's going to be a list arrow array. And that's going to be, and I need to use an arrow here. Why do we need to use an arrow here and here? Because the struct array list is not actually, the list is not actually just a struct, it's actually a pointer to the struct. So I need to dereference it before I access the member, and that's why I need to use an arrow in these instances. All right, is there any questions about the print function? The easy function. It gets worse. I lied. It gets easier the more it gets worse. All right, so the stray list is also pretty easy. So how much allocation did we end up doing? How much allocation did we need to do for the whole array list? How many times did we call an allocation function in our create array list function? Dude, 5 times? 2 times, just 2 times. So how many frees do you think I'm going to need? Just 2. So what do I free then? What are the 2 things that I created? I created the array and what else? The array list. So I created the array and the array list. So let's go ahead and free the list, right? And then we'll free the array. All right, and what problem do we have here? Use after free. Very good. So what do I do to fix this? Switch the order. All right. I expect you guys will hopefully be able to find those issues on the test if I have any. Hopefully it won't be too bad. All right, and so that's it for those 3 functions. Those 3 functions are probably easier than the append. Append is probably the trickiest one, and let's go through that. So the append is something where we need to, again, check to see if we're full. If we're full, we need to resize, and then we need to put the element at position size, which is like the first empty location in the list, and then we need to update the size. So those are the kind of the 4 things that we want to do. So check if full, then we want to resize if full. We want to add element to n, and then we want to update size. All right. So let's do the easy one. Update size. How do you think we update the size? Do we need to do a reallocation? Was size allocated to begin with? No, I just like set to some integer. So I don't think we need to do a reallocation on it since it wasn't allocated to begin with. So what should we do then? Like, how does the size need to be modified if we're inserting a value? Size times 2? Yeah, we should just add 1 to it. So how do we add 1 to the value? Plus plus. That's it. Whew. Okay. 25%. That's not great, but we're getting places. So how can I add an element to the end of the list then? So like, where do the elements actually go? Like, what part of the list do they go into? Where do the values go? Into the array. So what do you think we should do to add an element into the array? We do list arrow array, and then what?
Array size.
List arrow size. What about it?
-1.
-1? Why -1?
To account for zero indexing.
So to take out the zero indexing, what if size is 0? If size is 0, where do we end up inserting this value at? -1. Can we insert it at position -1? I don't think we can. Let's get rid of that -1. That makes me a little uncomfortable. I'm like a little bit worried. Like I try to avoid like like since size can be 0, you want to be careful with subtracting numbers from it and then trying to index. That might be dangerous. All right, then if we don't need to do like I think we like mentioned on the paper that we want to insert its size. Like if I bring up the doc cam. So yeah, it says the first empty spot is at position size. So we want to insert at position size. So let's go ahead and just leave it as size. Oh, and look, it says list that is equal to value. Okay, so I think I know what we need to do here then. So I need to say list array at position size is equal to what? Value. And that's it. So that's half the code done. All right, we're really close now. So now we need to check to see if it's full. How do we check to see if it's full? An if statement? All right, so if what? If list arrow size is equal to list arrow capacity, then that means we're full. 75% of the way there. And now we need to resize. So how do we resize? We need to reallocate. So we do list arrow array is equal to what? What type is array? Is it a struct? Is this what it is?
It's an able pointer.
Alright, who here thinks this is right? I hear a lot of muttering. So who here thinks this is right? Who here thinks that this needs to be changed? Alright, a lot of people think this needs to be changed. Someone that raised their hand for thinking it needs to be changed. What does it need to be changed to? Yeah. In star. Why is it in star? That's what the array was at the top, right? Array is an int star here, so it should still be an int star here. Hopefully, fingers crossed. So let's go ahead and make this an int star then instead. Alright, and then what do I need to do then? Realloc. Anything after realloc? Parentheses, yeah, alright. Inside here, what's the first argument going to be for realloc? We talked about this earlier today, right? The first argument is what? The pointer, and then what's the second argument? The size. Okay, so what's the pointer that we're going to be reading from for this reallocation? List array. Alright, and then what's the new size going to be? List capacity times 2, exactly. Alright, but now we need to update the capacity. So let's go ahead and do that. So list arrow cap times equals 2. And that is the entire append function in a nutshell. Oh boy, that was a lot of code and not a lot of compiling. I hope this works. So GCC array list dot, oh wait, what did I call this? I think we called it like, let me actually write it because I have a bad habit of not doing that. So it's called array list new dot c biscuits. Alright, what did I forget? Something important. The includes. Standard with. Standard IO. Tragic. Alright. There we go. Wow. Okay, so it doesn't work on the first try, but it's never supposed to work on the first try. So let's see if this works. So what is it doing? It's expecting something. What's it expecting? Input. So what input do I give it? Value. So like 1, it didn't do anything. How many, like, oh, I have to give it a -1? Uh-oh. Oh boy. That's fun. So the realloc failed, it looks like. Dang. Let's see what's going on here. So we say list array. What did I do wrong? Does anyone want to tell me? No? Alright, what am I always supposed to do when I do an allocation? What's the one thing you should include when you're doing the size group thing? Size of. Okay. Tragic. Alright. times size of int. All right. Now we're trying to compile, and we'll try to rerun it. And then, so now what do I do? I gotta enter those ones again. Oh, look. Okay, good. Yeah, we can keep going. All right. 2, 3, 4, 8. -2. Oh wait, why didn't it quit? Oh, 0, 0 works. Okay. Oh wait. Why did it do a -1 as well? Oh wait. Oh, okay. So it printed out the -1. I don't want to do that though. Let's go ahead and fix that. So we're gonna say, how about if the value is not equal to -1, then we add it to the list. All right, there we go. Now we're good. All right, that works. On to the next program. So we're gonna talk about binary searches now. So this is the array list. I will post this example code to WebCourses. You'll be able to take a look at it. I actually have one that's like mostly complete on WebCourses that has like a different name. And it's probably coded a little bit differently, but it's mostly going to be the same. But what we want to do for today's class, or what I wanted to do for today's class, is really talk about the binary search. I didn't want to go through a full-blown array list either. All right, so binary search. So I think I mentioned probably in binary search in class, right? What's a binary search do? Yeah? It doesn't go in like sorted order, right? It goes like in its. So, okay, so if you're going relevancy based off of the value you're getting, then that actually might be interpolation sort. So we do use the value that we're looking for to look for the value. I know that sounds silly, of course you're gonna do that. But we use like a little bit more information than standard. So like, let's say the classic example that we have for this is like the dictionary problem, which is given a dictionary and then a word, find out the definition of that word. Does anyone have a dictionary at home? Like a paper one? Like, okay, 3 people, that's nice. Good to see what the world's doing to us nowadays. All right, but anyways, so like if you have a dictionary, like a paper version of it, not Google or whatever, or Python, the idea is that they have words in there, and every word has an associated definition. And I remember when I was a kid, someone was like, did you know gold was not in the dictionary? And I'm like, that's cool. And they're like, aren't you gonna like look that up? And I'm like, no, you told me it's not in there. And they're like, okay, this kid is like real special. But anyways, so for the dictionary problem is we're given some word, and we're given a list of words as well. And what we want to do is we want to find the definition of that word. So find the location of the word in the list. Now doing so is going to be really complicated. So if you were given this problem exactly as it's written, like what you would have to do to find the word is you would have to like look at the first word and see if that's correct, and if that's not correct, you'd have to look at the next word. And so you can imagine if you had a dictionary and you're trying to look for this word, the dictionary might have like 100,000 words in it. You'd have to like keep flipping through over and over again through all these pages to eventually find the word you're looking for. Now that can be really slow, yeah? Yeah, so if we knew like it began with like the letter Z or something like that, and we knew that Z is like at the end of the alphabet, we could just kind of flip to there and then look through it in that way. That's like called the interpolation search. So the binary search is a little bit different. So like the binary search is like, imagine we don't know what the alphabet's like. So it could be the case that you know that all the words are like evenly distributed, and you know like roughly the end or like whatever is going to be like in the middle of the book, and you can go ahead and like kind of search in that location. But what if you had a dictionary where like maybe most of the letters, like maybe most of the words begin with the letter E? If that's the case, then that means you're going to have like the situation where the E's are really, really thick, And if you're looking for something that's like, you know, F, you might look near the beginning of it, but then you'll end up like with an E section. It's like, oh, that's not what I'm looking for. So maybe we'll look like a little bit further, and it's like still E's, and you just keep looking and looking for E, like, you know, this F word, but the problem is like the E's like take up the majority of the dictionary. So if we don't know the density of the dictionary, then we have a little bit of a problem. If we know the definition, the density of the dictionary, or if we know kind of like roughly like where things are located, we kind of use a different search method, but we're going to go ahead and imagine that we don't know the alphabet because I guess that's a good thing to assume as a computer scientist. So we're given some word, and we're given a list of words, but we're kind of, what I mentioned here is something that's really important, which is when you're given an actual dictionary, this list is actually sorted. We're given a list of words, but those words are given in a particular order. And that means we don't need to look at every single word. What we can do is we can do some elimination. So imagine we had 1,000 words in the dictionary. Now, and imagine in a really bad situation, the word is not in the dictionary. So if I were to use the original method where I look at every single word, how many words will I have to look at to find out that this word's not in the dictionary? 1,000 of them. Okay. So if you look at all the words until word found, words not contained take 1,000 examinations. So then there's this idea of if we know that it's sorted, we might be able to help ourselves a little bit. So if we know it's sorted, instead of looking at all the words, what can we look at that would help us eliminate a lot of words? Yeah?
Start at like half, and then start from there, so much words are right.
So the idea is we start at the midpoint. So look at the midpoint. And the idea is if we have sorted lists, we should know by comparison whether this word is either before or after this mid word. So if it comes before us, if the word that we're looking for is earlier, then so the midpoint is roughly at the 500 mark. So we look at the 500th word, and if we have a array, it's really easy to find the 500th word. If you have a dictionary, it's maybe a little bit tricky to find the 500th word, but you can roughly look in the middle of the actual plain book dictionary, and you can see like what words in the middle there. And then if we need to go into a higher point, why do we need to go into higher? So when do we need to go into the later? So let's imagine we have a word we're looking for zebra. All right, and imagine the middle word is like Mason. So this is our target, and then we find Mason. All right, so using this information, what do? Do we want to search at the beginning of the dictionary? No, we're not going to want to search at the beginning of the dictionary. Why aren't we going to want to search at the beginning of the dictionary? Could the word occur before this Mason? Could zebra happen earlier? Could it be any one of the 1 through 499 words? No, why not? Because we're assuming it's sorted, right? So that means zebra couldn't occur anywhere before Mason. Zebra has to be after Mason. So that means we can eliminate that first half of the dictionary. We basically throw away that half, and now we don't need to look at 1,000 words anymore. Now we only need to look at 500 words. So now we have only 500 words in our dictionary that we actually need to consider. We went from 1,000 words down to 500 with one lookup, or one comparison. Which is great. And the thing is, we don't have to stop here. We can repeat this process. We can do one more lookup. So if we were to stop now, imagine we were now to do our linear search. Imagine we were to look at every single word. How many words would we have to look at total? 500? Is that really the total?
501.
501. Why is it 501?
Because we just did one.
Because we did this lookup, right? So we're going to have to do 501 lookups at this point. So 501, but we can maybe do better. So we can do better by splitting this into two halves, by looking at the middle of this group and then seeing which side we need to go on. So what we can do is split this into two halves, and we can figure out if we need to go further or if we need to go earlier based off of the ordering. So if we ended up suppose we're looking for zebra, and we find ZYYXXX or something like that. I don't know how to spell X, or write X again, to say. That's probably not a word, but like, if we found this word and we're looking for zebra, do we want to like look after the set of words? No, we want to like look in the earlier section. We don't need, if we ever get to this point, we know that we definitely can't find it anymore. So by looking at this, we can eliminate another half. We can go ahead and eliminate like the last half of the dictionary. So you only need to look at earlier values. It's going to be somewhere in between Mason and this thing. I don't know how you have like 5 or 250 words, I guess, that begin or they're after this word lexicographically, but like maybe you have a really weird alphabet. But that means that by doing this one more lookup, we can go ahead and take it from 500 down to 250. And so this is using one more lookup. So how many lookups would it take now total? Is it 251? It's 252. Why is it 252? We looked at this one and we did this one. Yeah, we did 2 lookups. All right, so then we can repeat this process. And we go maybe from 250 to 125. How many total lookups? Yeah, so we do one more, so we have 128. And then we can do one more. What happens if we divide this by 2? We get like 62, 63. Let's just round up. We'll say 63. We'll assume like maybe we're back. Of course, like in practice, you can argue this will be 62. But so we'll imagine that this is 63, and it took one more lookup. So how many lookups did we take total then? 1, 2, 3, 4 plus this 67. All right, and then we can do one more lookup, and then what does this become? 32. So for a total of 1, 2, 3, 4, 5. 5 plus 32 is 37. This is still better than the previous one. It's like this is the best result we have in the number of lookups we need to do. And we can keep doing this. What do you think the smallest value we're going to get to is? Do you think we can get this down to 1? Why can't we get this down to 1? We already did one lookup, right? Could we get this down to like 4 or 5? No, because we already did at least 5. So it's going to be at least 5. Let's keep going. So we can go ahead and do another one. We do one more. We're now at 16. So that means that it's done 16 plus 6. So this is going to be 22 lookups. We do one more lookup. We are down to 8, which means it's going to be 7 plus 8. That's going to be 15 lookups. We do one more. We get down to 4, and then so we do one more lookup. We get to 4. We do 4 plus 8. That's going to be 12 lookups. Oh god, this is getting really bad. We do one more lookup. What are we going to get down to with 4? 2? All right. And then what's going to be the total then? It's going to be 11 here. If we do one more lookup, what's going to happen? It's not actually going to change any. If we do one more lookup, it's going to go to one lookup here and one word left in the dictionary, and that means it's still going to be like 10 plus 1, so it's going to be 11 lookups still. So really, when you get down to like 2, really when you get down to like 8, it's normally in better practice just kind of like search the list or something like that. I think like most people like hard code it like 5 or something like that. But the idea is like once you get to some point, you can kind of like just search aggressively like the same way. And the reason why is because it takes like time to go ahead and find the midpoint. So it might be better just to do a comparison depending on like how expensive the lookup is. If a lookup is really expensive, then keep going all the way. But this means that we have to do like only 11 lookups. So 11 is like really weird. That's crazy that it takes that few. My question is, if we use this method, and hypothetically we had something like 1 million words, how long would it take? How many lookups would we need to use if we were to do this same procedure? Does anyone know off the top of their head? Roughly speaking, yeah. It's going to be logarithmic. So why is it logarithmic? So the reason why it's logarithmic is because every lookup we get, admittedly, it has the dictionary size, right? So you can think of, if we had a dictionary of like the maximal size with some number of lookups. So imagine that we had, so imagine we had to do, we were able to do k lookups. My question is, what's the size of the dictionary we could use? So if we had only one lookup, how many words could we have in our dictionary? Well, we couldn't really do 2 because like if we had 2 and we looked at one word, it could be the other word if it like is on that size. So we really can only do like if we have like only one lookup, we can only do a size of 1. If we had 2 lookups, how many dictionary words could we support? So we can actually support 3 in this instance. The reason why we can support 3 is because we look at the middle value And then we can either be on this side or we can be on this side. Do you agree with that? So my question is, how many can we do with 3 lookups? 5? I heard someone say. Who here thinks it's 5? Alright, who here thinks it's another value besides 5? Alright, what value would it be then? 7? Why do you think 7? Who here thinks it's going to be 7? Like a few more people, but not a lot of hands. Alright, it is going to be 7, but why is it going to be 7? Okay, so we can do the 3 on this side, and we can do the 3 on this side, and either of those can be solved using 2 lookups, right? And then we have the 1 lookup that we can do in the middle. So we can do this one, or we can do this 3 and this 3, right? So then how many is going to be the next instance? Is it 11? So we can have 7 on this side and 7 on this side, and then we can have 1 in the middle, right? So how many is that? 15. So how many can we do? 15, not 18. How many can we do in the next lookup? 31. All right. And the reason why it's 31 is because what's the pattern going on here? We multiply by 2 and add 1. This is really close to the power of 2. If we look at powers of 2, we have 2, 4, 8, 16, and 32. Is there a relationship between these 2 numbers? It's a power of 2 minus 1. That's exactly what we have going on here. So that means with k lookups, we can do, roughly speaking, 2 to the k minus 1 dictionary size. So we can do 2 to the k minus 1 words. So if we want to find what k is based off the number of words, so if I say we have this many words, how many lookups is it going to be? We want to basically solve for k. So what we can do to solve for k, like this is equal to the number of words. Like I guess I should say this is really like w here. So what we can do is we can like add 1 onto both sides. We get 2 to the k is equal to w plus 1, and then we get k is equal to log base 2 of w plus 1. So that means, though, roughly speaking, the number of lookups we'll need to do is logarithmic, which is very, very good as opposed to doing just w lookups. So that means if we're looking at something that's the size of 1,000,000, for those of you that don't know, 1,000,000, roughly speaking, is 2 to the what? What is 1,000 in powers of 2? I mentioned this like once in class a long time ago. So 1,000 is roughly speaking equal to 2 to the what number? It's 2 to the 10. That's pretty close to what we had before. Like the 10 here kind of represents how many lookups we kind of need to do. We had to do like 11 lookups is what we said. 10 and 11 are pretty close. It's off by 1. So it's like reasonably understandable that you might get a little bit confused there. So if we're trying to find out what 1,000 squared is, so if I square this side here and I square this side here, what do we end up getting 2 to the power of here? This is equal to 2 to the 20. So that means with 1,000,000 words, we only need to basically double the number of lookups. So if we square the number, like we're not squaring the number of lookups we do, we actually only kind of double that. So that means like if we get really, really big dictionaries, like if we have a dictionary with 1,000,000,000 words, it'll only take up 30 lookups. So like really practically speaking, with how 64-bit machines work, you only need really to do 64 of these lookups, like 64 of these calculations when you're doing these binary searches, at least when you have the right order of magnitude set up for your search space. And we'll go over examples of binary search next time, and we'll do like a little bit of math analysis. Unfortunately, we weren't able to get into math today, but